Hello everyone and welcome back. My name is Mr. Cobalt, and in this video we're going to be going over how boiling point temperature changes due to external pressure changes. So let's get into this. So to remind ourselves, we talked about boiling and how boiling occurs in my last video. And so to recap a little bit, the boiling will occur. The boiling point is the temperature at which the internal vapor pressure, the vapor pressure of the liquid, is equal to the external pressure. Until that happens, you won't get boiling because the external pressure will be greater than the internal vapor pressure, and so the bubble will collapse and it won't form long enough to reach the top of the surface, right? So we saw that vapor pressure is going to be determined by the vapor pressure at which you get boiling is going to be determined by the external pressure. Well, what happens if you change the external pressure? If the external pressure acting on the liquid changes, then the boiling point of the liquid is going to change. Well, why is that? Let's go through the steps. So you decrease the external pressure above the liquid, right? So we're going to decrease that pressure, the external pressure above the liquid. What's going to happen? Well, then that means that a lower vapor pressure in the liquid is needed to form bubbles, right? Because remember, in order to form a bubble that's going to stay and then float to the top of the liquid, which is what we call boiling, the vapor pressure has to be at least equal to the external pressure. If you lower the external pressure, then the vapor pressure that you need inside the bubble in order to get that bubble to form is going to be lower, right? So you don't need as high of a vapor pressure. If you don't need as high of a vapor pressure, then you don't need as high of a temperature that's needed to get to that vapor pressure, right? So if you lower the vapor pressure needed, then the temperature that you need in order to reach that lower vapor pressure is also going to be lower, right? And then that refers to that brings us to a lower boiling point, right? So the lower boiling point temperature is going to be the temperature at which you need in order to get to that vapor pressure that's needed to equal the external pressure, right? So lowering the external pressure will decrease the boiling point. If you increase the external pressure, then you increase the boiling point. And again, remember, the boiling point is defined as the temperature at which water boils, or another way to put it that we've been talking about is the temperature at which the vapor pressure in the liquid is equal to the external pressure, right? So changing the external pressure is going to change the boiling point, or the temperature at which water is going to boil, or at which you're going to form bubbles that are going to stay. So this will explain why it takes longer to cook food at the top of a mountain, right? If you go backpacking or if you go mountain climbing, you'll notice that if you cook food at a higher elevation, then you're going to need longer time to cook the food. It also explains why food cooks faster in a pressure cooker. If you've ever used a pressure cooker, food will cook faster than normal. Well, why is that? Well, in the mountain, you can realize that when you climb up the mountain, the air pressure is going to be less because you have less atmospheric pressure pushing down on you. So the higher you go up in the atmosphere or in elevation, that means you have less atmospheric pressure pushing down on you. So less atmospheric pressure means that you are going to, it requires a lower vapor pressure to reach boiling, right? So it means you're going to boil water at a lower temperature. So at the top of Mount Everest, water will boil at about 72 degrees Celsius, right? So at 72 degrees Celsius, it's a lower temperature. That's not as hot when you're cooking your food. So because the temperature is lower at cooking at the boiling temperature, then you're going to need to cook it longer in order to fully cook the food, right? Same thing for a pressure cooker. If you put food in a pressure cooker, you can increase the pressure inside the pressure cooker, right, to higher than normal, right? So to higher than 1 atmosphere or higher temperature or higher pressures. If you increase the temperature, the external pressure inside your pressure cooker, then that's going to mean that you're going to need a higher vapor pressure to form the bubbles needed for boiling, right? Which is then going to need a higher temperature needed for that to happen. And so it's going to raise the temperature, it's going to raise the boiling point. So when you cook your food in a pressure cooker, if the pressure cooker is definitely, it gives you a higher pressure, external pressure than say 1 atmosphere, then you're going to need more. You're going to need a higher temperature. You're gonna cook your food at a higher temperature, and therefore it's going to take less time to cook the food because you're cooking at a higher temperature, right? So so the idea here is that when you have food cooking or boiling at a certain temperature, the extra energy that's coming from heating your food, right? Like, so if you're cooking it on a stove or something like that, once you get it to boil, that extra heat that's going into the boiling is not increasing temperature, but going into increasing the potential energy of the liquid, right? So as long as you're supplying energy, that energy is going into the boiling and increasing and allowing for the potential energy of the molecules to occur. And potential energy is tied to the positioning of the molecules, right? So if you allow the molecules to spread apart, you're increasing the potential energy of the molecules. And so that energy that you're going into the boiling isn't going into the kinetic energy of the molecules, right? It's going into the potential energy of the molecules to allow for that expansion and that turning into a gas, into the vapor phase, right? So during the boiling process, the temperature of the liquid stays the same because the kinetic energy, the average kinetic energy, is not changing during the boiling process. It's the potential energy that's changing during that process. Okay, so let me write in my next little segment of this video, I'll put a graph up and I'll talk about the graph, so stay tuned. Okay, so here's the graph, and so we'll talk about the graph and with respect to what we've been talking about. Now, this graph is, not drawn perfectly to scale, but it's good enough to show exactly what I was talking about before. So here you have the vapor pressure of the substance, right? So measured in kilopascals. And on the bottom here you have the temperature in Celsius. So here you can see as the temperature increases, the vapor pressure of the liquid increases as well. And so remember, in order to get something to boil, you need the vapor pressure of the liquid to be equal to the external pressure that's out there. So here, if you'll see the external pressure. So this is the external pressure, but also the vapor pressure, you want that to be equal to the external pressure in order to get that to boil. So even though this is vapor pressure in kilopascals, it also relates to the external pressure because we're assuming that they're going to be equal in order to get the boiling temperature. So you could see that this temperature here is the boiling temperature, and this is the atmospheric pressure / vapor pressure of the liquid, which has to be equal in order to get to the boiling temperature, if that makes sense. Okay, so here you can see that as you go up in atmospheric pressure, as the external pressure increases, therefore your vapor pressure also has to increase in order to get to boiling. And you'll see how that's related to the temperature at which you will get that boiling, right? So here is the temperature related to the vapor pressure you need at that temperature to get to boiling. And so you can see that this curve here, as the vapor pressure increases, the temperature you need to get to that vapor pressure also increases. So you can see here, this is 101.325 kilopascals. This is at 1 atmosphere, which is typically what you were at sea level. So if you're close to sea level, this is the atmospheric pressure. So this would be the vapor pressure you would need internally, to the liquid vapor pressure you would need in order to get those bubbles to not collapse, and then you get boiling, right? So, and this requires 100 degrees Celsius. So at sea level, water will boil at 100 degrees Celsius because the external pressure at sea level is 1 atmosphere. And so therefore the vapor pressure has to be equal to 1 atmosphere to get it to boil, right? Okay, so now what if you're up in the mountains, right? So if you're up in the mountains, right, like Mount Everest, your external pressure is going to be much lower. So here, like say at the top of Mount Everest, the atmospheric pressure is about 0.34 atmospheres. And so you can see that the temperature at which you would need to reach that vapor pressure of 0.34 atmospheres is about 72 degrees Celsius. So you would have to raise the temperature only to 72 degrees Celsius to get the water to boil, and then you can maintain that boiling at 72 degrees Celsius, right? So because the temperature is lower at that higher altitude or lower atmospheric pressure, you're going to need to cook the food longer at that lower temperature, right? Now, if you're using a pressure cooker, you could increase that pressure inside the pressure cooker to double the atmospheric pressure, right? So the atmospheric pressure is at 1, you could double it to 2, right? So at 2 atmospheres or 202 kilopascals, right, you would need to get the vapor pressure to that height. So in your pressure cooker, you are raising the pressure inside the pressure cooker to maybe about that much. Let's assume 2 atmospheres. Well, at 2 atmospheres, in order to get the water to boil, right, you could get it to boil at a higher temperature, 100, like maybe a little bit over 120 or 122 degrees Celsius. So your water will boil at 120 degrees Celsius at that higher pressure inside the pressure cooker. So you could actually get your food to cook at a higher temperature, and so that therefore you don't have to cook it as long. So here's a nice graph to kind of show you the relationship between the boiling temperature that you would need versus the vapor pressure that's tied to that boiling pressure. So changing the external pressure requires a different vapor pressure, which is associated with a different temperature, right? So I hope this helps. Also, by the way, I just want to point out that anytime this graph is showing us that the vapor pressure or the boiling point is dependent on the external pressure, right? So anytime you report a boiling point, you should report the external pressure because boiling point is dependent on external pressure. Now, a lot of times that pressure is not reported, and if it's not reported, it's assumed to be at a normal boiling point. And what do I mean by normal boiling point? Right, normal boiling point is defined to be at 1 atmosphere. So if you're reported a boiling point of 100 degrees and there's no pressure indicated, then you can assume that they're assuming 1 atmosphere and they're giving you the normal boiling point. So normal boiling point is defined as the boiling point of a substance at 1 atmosphere, right? So the normal boiling point of water is going to be 100 degrees at 1 atmosphere, right? If we're talking about something else like maybe hexane, hexane's boiling point might be 69 degrees at 1 atmosphere, right? So if I report a boiling point of hexane as 69 degrees Celsius, and I don't tell you the atmosphere, or I don't tell you what the atmospheric pressure is, you can assume that it's 1 atmosphere, and what I am reporting to you is the normal boiling point of hexane, right? So anytime you're given a boiling point without a reference to an atmospheric pressure, then it's assumed to be the normal boiling point at 1 atmosphere. Otherwise, you would have to report the atmospheric pressure if it's not at 1 atmosphere, right? So that's the use of this graph. I hope this use of graph was helpful in explaining the relationship between the boiling point temperature and the external pressure changes. Okay, So the next thing I want to talk about is the relationship of this to different attractive forces. So stay tuned. Okay, let's now talk about the relative boiling point temperatures in relation to the strength of attractive forces. So we talked about before how in order for a molecule to break free from the to break free and become a vapor, to go to the vapor phase, it needs to break free of those attractive forces of the other particles or molecules at the surface, right? So if the strength of the attractive forces are stronger, then that means you're not going to get as many particles breaking free from the surface in order to become in the vapor phase, right? So let's talk about this step by step. So you've got these molecules, right? So you've got molecules, they all have attractive forces. And so we're talking about like breaking free and creating a vapor in the bubble, right? We're talking about boiling point and we're creating that bubble. And so remember, we need the vapor pressure inside the bubble to be the same as the external pressure, right? And that vapor pressure requires molecules or particles to break free from the liquid phase and become vapor so that they can bounce around and create pressure. So what happens when you increase the strength of the attractive forces? If you have something that has stronger attractive forces, right? We're going to increase the attractive forces. Well, what does that mean? That means that you're going to get a decrease in the rate of evaporation. Well, why? Well, because if you have stronger attractive forces between molecules in the liquid phase, it's going to be harder at any particular temperature for those molecules to break free and become vapor molecules, to become to be in the vapor phase, right? So you're not going to have as much evaporation occurring. So because you're not going to have as many molecules that are going to have the needed momentum or the needed kinetic energy to break free from those attractive forces. So you're going to have a decreased rate of evaporation, which means that you're now going to have a decreased rate of condensation at equilibrium, right? So why is that? Well, if you have less particles in the vapor phase because less of them can break free from the surface of the bubble, right, and go into the vapor phase, well, that means that you're going to have less particles that are going to bounce around and then go back into the liquid phase. Remember, the rate of condensation is going to depend upon the number of particles that you have in the vapor phase that is bouncing around. Less particles means less rate of condensation, right? So if you have a decreased rate of evaporation, that means you're going to have less particles in the vapor phase, which means that you have a decreased rate of condensation at equilibrium. Because remember, at equilibrium, the rate of evaporation is going to be equal to the rate of condensation. So if you have a decreased rate of evaporation, then you're also going to have a decreased rate of condensation at equilibrium because they have to be equal. Which then goes to the lowering of the concentration of vapor needed to reach a lower rate of condensation. So that's what I was talking about earlier, right? So the rate of condensation is based upon the concentration of the vapor, right? So if you have a lower rate of condensation, then you don't need as many particles in the vapor phase in order to have that rate of condensation, if that makes sense, right? So you're going to have a lower concentration of vapor in the vapor phase, right? Because the rate of condensation is lower, you don't need as many particles in the vapor phase, right? Which means that you're now going to have a lower vapor pressure at that temperature, right? So lower particles, number of particles in the vapor phase inside your bubble means that you're going to have a lower vapor pressure inside that bubble at that temperature, right? So, which means that now you need a higher temperature to get those particles to break free from the attractive forces and increase the number of particles in the bubble in order to get that vapor pressure up to where it was before, right? At if you had a weaker attractive force, right? So now, because you have a increased strength of attractive forces, now you need a higher temperature in order to bring the vapor pressure up to the external pressure, right? Because when we increase the strength of attractive forces, that ultimately led to a lower vapor pressure in the liquid, in the bubbles, which means that you would need to now raise the temperature in order to get that vapor pressure up to the external pressure, which means that now the boiling point, the temperature at which water boils or at which the liquid boils is going to be increased, right? And so you can see that here in this little graph that I drew. It's not, again, it's not to scale, but it's as good as I can get it, but hopefully it's enough to see the point that I'm trying to make here. So here we are comparing acetone and water. Acetone has weaker attractive forces. Acetone has dipole-dipole interactions, whereas water has hydrogen bonding. And hydrogen bonding is a stronger attractive force than the dipole-dipole interactions of acetone. And so we can see here is that here we have, again, the temperature needed to get to boiling, and then this is the vapor pressure. So we're looking at the temperature needed to get to the vapor pressure that's going to meet the external pressure for boiling, right? So what you can see with acetone is that it starts here at in the negative degrees Celsius. And as you're raising the temperature here's our 1 atmosphere. So this is the 1 atmosphere of pressure. This is where your normal boiling point would be at. And you'll see here that in order to get to normal boiling point for 1 atmosphere, so if you're trying to boil acetone at sea level, right, at 1 atmosphere, you would have to raise the temperature up to only about 56.5 degrees Celsius. So that's what acetone boils at. And then water, because it has stronger attractive forces, you're going to have to raise that temperature higher to get to the normal boiling point of water, because you have to add more energy to break free from those stronger attractive forces in order to get more water molecules to be in the vapor phase to increase that vapor pressure. So here you have to increase the temperature up to about 100 degrees to reach the same atmospheric pressure as acetone. So acetone requires less energy in order to get it to boil, because the interactions, the attractive forces between the acetone molecules are weaker, and so less energy is needed to bring it up to a boil to overcome those attractive forces and to get that vapor pressure. Whereas for water, you need more energy to get those molecules to break free, and so the temperature is going to be higher. So you need a higher temperature to get to the vapor pressure that's going to be equal to the external pressure of the atmosphere at sea level here at 100 or 101.325 kilopascals, or 1 atmosphere. And so you could see here that the normal boiling point, remember, normal means at 1 atmosphere of external pressure. Right, so at 1 atmosphere of external pressure, the normal boiling point of water is 100 degrees, whereas the normal boiling point of acetone is 56.5 degrees Celsius. So that's it for the video. I hope this all made sense. If you like the video, then please like the video, hit that like button somewhere. Also subscribe to my channel somewhere up there, hit that button. And then also leave a comment down below. Let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me, and have a great day.